Hello everyone, good day, good evening. I'm sorry, I'm just pressing the record button. And welcome to another episode of Differential Equation with Japi. And I hope you guys are excited. I'm sorry, we're gonna skip a few lessons. I haven't made a video for Ronskian and Introduction to Higher Order Differential Equation because I'm too busy. I've been busy with checking my students' exams. I've been busy with, well, basically I'm also paneling from some other capstone. But I promise when I have time, I'll make some of those videos. I'm just making these videos because this is the current topic I'm teaching to my students, and I hope my students are watching, and I hope they're learning from me. Okay, I'm also happy if they're learning from others, but I'm gonna be sad if they're not watching. But no, I'm just happy if they're learning. Okay, well, I'll be happy if they follow and subscribe. Yeah, let's go. Anyways, okay, so let's move on to our lesson. Or we're gonna be tackling homogeneous linear higher order differential equation. We're done with first order. Okay, when we say first order, let's give an example. First order differential equation y prime minus 3y. We're gonna use that later, but that is an example of y prime higher. That's an example of first order. An example of higher order. Okay, an example of higher order is y double prime plus 3y. That's higher order. 3y prime minus 9y is equal to x squared, or we can like 99 x cubed or 888 x. That's a higher order differential equation noted by the y double prime. Okay? Okay. So we're tackling about higher order differential equations, homogeneous and linear. Okay? This is my third take. You see that there's checks there. Okay? So when we say homogeneous, okay, any other terms that is not multiplied to y is 0. Okay? And all the terms with y and its order, y and its derivative, okay, is on the left side or probably on the same side. Okay? So this will be an example of a homogeneous equation. Okay? This will be an example of homogeneous equation. This will be an example of, let's say, y to the fifth order plus y quadruple prime is equal to 0. That's an homogeneous equation. Okay? But when we say linear, okay, let's go back. When we say linear differential equation, when we say linear differential equation, okay, the degree of our derivative and its dependent variable are 0, but because this is second degree, this is not linear or non-linear. Okay, non-linear. Our third example is linear. Okay, we're gonna have another example. Let's say y. Okay, let's have black ink. Y triple prime plus 3y double prime plus 2xy prime plus y is equal 0. That's homogeneous linear higher order differential equation. Okay, but we're tackling about constant coefficient. So anything that is multiplied to your y or your dependent variable should be constant coefficient, and if it's a variable, that's not constant. Okay, so this is not constant coefficient. Y double prime plus 3y minus 9y 3y prime minus 9y is equal to 0. Now that is a good example of homogeneous linear higher order differential equations with constant coefficient. Okay, so that's a very long term and topic, but that's our topic for today. Okay, so we got two examples of differential equation: homogeneous linear and constant coefficient. So the first one is first order. The second one is second order. Okay? So the goal is to solve for second order. But we're gonna solve for first order first. Because we already learned about first order. And we can determine its general solution. Okay? We can determine its general solution using Yepex-Depex. Yepex-Dex, Kebex-Dex, Kebex-Dex, Kebex. This one. We can easily solve for it. Probably I'll just speed up the process. E, where P. Okay. I'm gonna delete the solution. Wait. Okay. I'm gonna delete the solution. We now know that our answer to our first order differential is C e raised to 3x. And if we try to change this 3 into, let's say, 4, your answer is gonna be 4x. Okay? That's your assignment. I'm not gonna solve it again, but that's your answer will become 4x. Okay? Okay? Now there's a pattern. Okay? We're gonna notice a pattern. Okay? Okay? So, in order to analyze what will be our answer for our higher order, we're gonna be transforming our first order into differential operator form. Okay? Differential operator is basically another form of your y prime into differential operator y, capital dy. Your y double prime is equal to d square y. Your y triple prime is equal to d cube y. So basically, and so on, right? So basically, we're transforming our derivative or order into degree of d differential operator. So our y prime minus 4 will become, or maybe let's transform this into a, or to m, right? To m, right? To m, right? And our answer will become mx. Okay, our answer will become mx, right? So differential operator y for y prime minus my is equal to 0. Okay. So, the differential operator is treated as a variable but also a derivative. In a way, you can separate y into your equation. Okay? It's treated as a variable. Now, knowing that we can separate y, okay, we now can notice that, okay, we can find a function of d in the solution. Our first order differential equation created a binomial. Okay? Okay, I'm gonna go back to the second order. Okay? I'm gonna go back to the second order. Okay? So, our second order example. Okay? Let's turn that to differential operator. dy square y plus 2y. 2dy. Okay? Minus 3y is equal to 0. Separate y. D square plus 2d minus 3, okay, is equal to 0. Okay, noting that our d square, it's a quadratic equation squared, right? It's a squared, right? And our m, okay, our m, okay, our m is basically a root of our binomial. And when we say a root, if you substitute m to your, if we let m be the roots of the equation, okay, m minus m is equal to 0, okay, 0, m is now a root of your equation. And in our example, m is 4, right? So if we have d minus 4 or m minus 4, m is equal to 4. 4 is now a root. And our general solution will become c e raised to 4x. Okay, the answer from before. The answer from before. Okay? Okay, for second order, knowing that that's quadratic, okay, let m be the roots. Why? Why do we need to let m be the roots? Okay, so for example, if we know that our solution, okay, we know that our solution will become constant, e raised to mx, okay, e raised to mx. If we substitute e raised to mx in our, okay, in our differential operator form, okay, if we substitute e raised to mx on our differential form, t square y y is equal to e raised to mx, right? Substitute that. So e raised to mx plus 2d e raised to mx plus 3 e raised to mx, okay? If we differentiate e raised to mx twice, it will become m squared e raised to mx. Differentiate e raised to mx once, 2m e raised to mx plus 3 e raised to mx is equal to 0. Cancel 3 e raised to mx, take out. M squared plus 2m minus 3. Okay. Okay. M is now a root of our differential operator, right? See that? M squared, 2m, d squared plus 2d minus 3. Basically, we just substitute m and 2. Okay? And that quadratic equation is polynomial or factorable polynomial. M plus 3, m minus 1 is equal to 0. Okay? We can now safely assume, okay, our general solution is c1 e raised to 3 negative 3x plus c2 e raised to x, knowing that our root is negative 3 and our another root is positive 1. Okay, root is what you call a value or a number that if we substitute to our polynomial, okay, if we substitute negative 3 on this equation, negative 3 plus 3, it will become 0. Our polynomial will be true. 0 is equal to 0, or our polynomial will be 0. That is the definition of a roots. That's algebra. Okay? And now this is our general solution. Okay? Okay? And this is what you call case 1. Distinct roots. Okay? Okay? Distinct roots. Okay? Another example, maybe that's too much explanation, right? Let's just solve. Okay, let's have another example. Okay, I hope you guys are taking all the information in. But I mean, let's just solve for a differential equation. Okay, so let's go for number 2. Okay, we're gonna do the same format, right? We're gonna do the same format. Okay, we convert to differential operator, find the polynomial, and solve for the roots. Okay, convert into differential operator. 3d squared y minus 4dy 4dy minus 12 y is equal to 0. Separate y, d cubed plus 3d squared minus 4d minus 12 is equal to 0. Determine the polynomial. D cubed plus 3d squared minus 4d minus 12. Okay. Let m be the roots of the equation. Okay. So we can substitute m cubed plus 3m squared minus 4m minus 12. Are you guys seeing what I'm writing? Maybe I'm too far away. Okay, but I'm gonna scooch. Not so much. Not so much. Okay. I'm still coughing. I'm gonna move a little. Okay. This now equal to 0. Okay. Now we have to determine the root. Okay. but this is quadratic equation. I'm gonna do this via synthetic division. Okay. Now, to determine the root of an equation, we can guess the root of equation by dividing the last term with the first term factors. Okay. What do we mean? So let's say the term, okay, the factors of negative 12 is positive or negative 12, positive or negative 1, right? Multiply positive 12 and negative 1, that's negative 12. Okay? Positive or negative 3, positive and negative 4, positive or negative 2, positive or negative 6. That is all the possible factors divided by positive or negative 1 by the first term. The factors of the factors of the constant term divided by the factors with the highest degree of m term. Okay? Okay. So, we're gonna guess. I'm gonna do a trial and error. Now, because this is negative 4m and negative 12, I'm gonna do negative 1. Okay? Negative 1. Okay? If we substitute negative 1 to our equation, alright? So, negative 1 cube, that will become negative 1. Positive 3, negative 1 square, that's positive 3. Negative 4, 1, that's negative 1, that's positive 4. Negative 12, oh, it's not 0. Okay, it's not 0. Okay? It's not 1. Okay? How about negative 2? Negative 2. Negative 2. Negative 2. Let's say negative 2. That will negative 2 cube plus 3, 4, minus 4, negative 2, negative 12. Okay? So this will become negative 8, positive 12, positive 8, negative 12. It's 0 out. Okay? Negative 8, positive 8, cancel. Positive 12, negative 12, cancel. Okay? So one of our root is negative 2. Okay? Okay? In order to transform this polynomial into factors or to binomials, we can use synthetic division. Okay? So let's write down 3, negative 4, negative 12. Synthetic division. 1 multiply to negative 2, negative 2. Add 1. Multiply to negative 2, negative 2. Add negative 6, multiply to negative 2. That's positive 12 is 0. Meaning, one of our root is negative 2. One of our factors is m plus 2. This will become m squared plus m minus 6. If you don't know how to synthetic division, I recommend you guys learn synthetic division. Okay? Equals 0. Okay? And our quadratic equation left is factorable, right? M plus 2. M minus plus 3. M plus 3. M minus 2. Okay? Is equal to 0. Okay? Meaning our roots is negative 2, positive 2, and m negative 3. Okay? Okay. Now, there's a lot more easier way to get our root. Okay? There's a lot more easier way. For example, if we have a calculator, we can do shift solve. Okay? We can do shift solve. But, okay, if you guys are like students and if you guys are solving or you need a solution, sometimes in mathematics, calculators are not allowed. Because it's sassy. You know, you don't know. Right? We type the degree, right? So, right? Let's say x cube plus 3 x squared minus 4x minus 12 is equal to 0. Okay? So, instead of m, I use x cube and I use shift solve. Okay? Let's say 1 million. Or I'm saying negative 300. Negative 3. Because one of the root is negative 3, right? And negative 2. Let's say negative 3. Okay? Then shift solve. Oh, or shift solve, negative 300. 3 million. Okay? 3 with zeros. Okay, it will be a lot harder to solve, but if we press enough, the answer will become x is equal to -3. And if we press shift solve again, that is -3 again. Okay, shift solve has a one common flaw. Okay, usually calculators will only give you one value, and it will give you the closest value that you substitute to your solve for x. Let's say 1 million, the closest value for 1 million is 2. So it gives you 2. Let's say I'm gonna substitute like -9999999. The closest value to -9999 is 3 or -3. So the roots is even. So we are not able to solve for -2. We can use mode 5. Look for the polynomial 4. 4. Because mode 4 is for cubic. So we can substitute our terms. Oh, sorry. Okay. 1 for our cubic coefficient. 3 for our cubic coefficient. -4 and -12 for our constant coefficient. Okay. Your calculator now will give you the roots. Okay. Now we give you the roots. -2, -2, and -3. Okay. You can use calculator, but if calculator is not allowed, you have to learn synthetic division. Okay, and if that's not factorable, you have to learn quadratic equation. Okay, if you are not able to factor your polynomial, okay, or your quadratic polynomial. Okay, anyways, that's our root. The answer will be become c1 e raised to -2x plus c2 e raised to positive 2x plus c3 e raised to -3x. Okay, you just put your m into the constant. Okay, we have 3 constant because we have third degree differential equation. Okay, so then if your distinct roots, okay, we put the m or we raise e to mx. Okay, the answers will become e raised to mx, and one of them is -2 m1 plus c2 e raised to m2x plus c3 e raised to m3x. Okay, just substitute the value. Okay, and if we want more, if that's like 10th order, we're just gonna add more constant, multiply to e raised to mx. Okay, so that's our case number 1, distinct roots. Okay, distinct roots. Alright, let's solve for more. I'm gonna do a 2-part video, so we're gonna end here. I hope you guys learned something, and we're gonna continue to part 2 because I don't want to make the video long.